Hello, and this is our project showcase presentation for the object detection drone for Senior Design Spring 2023. For the team members in this project, we had Derek, myself, who's computer engineering, Cannon, who's also computer engineering, Jasmine, who's electrical engineering, and Kevin, who's optics engineering. This project was sponsored by the UCF Department of Electrical and Computer Engineering. They provided us funding for the drone components, and they also offered us areas for flight testing.
Our motivation and purpose behind this project was to develop a drone with object and distance detection abilities. Our effort was put into full flight control, machine learning, and optics systems for the drone to function successfully. For our requirements, we have 6 different specifications. The first one is the drone should be able to fly in all axes. The second is that the drone should be able to maintain an altitude, aka hovering. The third is that the sensors must measure distance from white objects a set distance with high accuracy. The fourth is the machine learning model must be able to classify objects within a relatively close distance with high confidence. The fifth is the drone must be calibrated to pass all pre-arm checks for the safety purposes. The last is the drone should only be flown indoors to avoid interference from weather conditions. And these are our block diagrams. On the left you can see the hardware diagram relevant to our project. You'll notice that the Raspberry Pi and Pico are the driving units for our project. And on the right, you can see our software diagram where the majority of the action is done within the active inferencing script. The first specification we'd like to go into is the drone build and design.
Before starting the build, I went ahead and placed each component without tying anything down to plan the placement of each item. The major items we see here are the bottom plate, the 4 legs, the top plate, and the Raspberry Pi. We also have the electric speed controllers that are placed underneath each leg, the motors that are placed on top at the bottom of each leg, and the vibration dampening plate, which would be at the bottom of the Raspberry Pi. Here we have just the bottom plate shown with the legs attached. The bottom plate is the power distribution board, so we did go ahead and soldered each of the electric speed controllers to the bottom plate and the power adapter to the bottom plate. And then the motors are going to hook into each electric speed controller. I went ahead and labeled the front side of the drone, and the front side of the drone will be the red legs. And now we have the flight controller, the Pi-Hawk, that we chose as our flight controller that was mounted onto the Raspberry Pi. First, we went ahead and mounted on a 3D printed placement holder for the Raspberry Pi and inputted the Pi cam into the camera mount that came with the kit.
With the drone build in place, we can now transition into the navigation and calibration portion.
We use the Mission Planner software for firmware installation and optimization on the PixHawk module. Mission Planner was also used for calibration of the accelerometer, compass, GPS, remote control, and the electronic speed controllers. Once the calibrations were all completed, I was able to test each of the motors in both unison and sequential, as well as determine the spin direction, which is crucial for proper flight and propeller placement. Finally, Mission Planner provided pre-arm checks for both physical and safety constraints before arming the motors and taking flight. Here are a couple of examples regarding the calibrations that took place while utilizing Mission Planner. The left image is the process of calibrating the accelerometers, in which the gyroscope was fine-tuned to provide stable flight in all 3 dimensions. The right image is the compass and GPS calibration, in which the software can detect the location of the drone, as well as obtain a strong enough satellite signal to arm the drone as required in the pre-arm checks in Mission Planner. Here is a simple demonstration of the drone successfully taking off and landing using the remote control after clearing all pre-arm checks and arming the drone.
The next subject is the distance detection. According to our specification, these sensors have to be able to measure a distance of up to 0.75 meters with a 0.1 meter accuracy or so. An infrared distance scanner or LiDAR scanner has been developed, as well as a series of infrared proximity sensors that will be arranged around the legs of the drone. These are going to let the drone know when an object is getting close, and it will give a signal to our camera to turn on and start looking for an object to detect, so it doesn't have to be recording constantly. Now, this has a reliable range of up to about a meter, but it can less reliably measure objects up to about 1.3 meters or so. In this first version, we can see the laser scanning across the target objects, and they're reporting the distance data on the computer screen. And as you can see, the distance remain the same on both colors, which is a really important thing, because this proves the scanner can accurately measure the distances regardless of color. In this next video, I have added an LED that triggers whenever the object is within a certain range that is given by the processor. The first video is within about a foot, and the second video is the target is set to 2 feet. Now this information is important because we want to be able to tell the camera when to start recording, so it doesn't waste too much data recording nothing. And of course, our final video shows this integrated with the drone itself, showing that it can still detect objects while upside down on the bottom of the drone. So this brings us to our PCB design, which controls all of these sensors that I've mentioned. The left side of the board controls the proximity sensors, and the bottom of the board is a Colpitts oscillating circuit that creates a signal that modulates at about 48 megahertz. This signal is then sent to both our laser and to our voltage comparison circuit on the right side of the board here. Now, this compares the modulation signal with the signal being recovered. And since analyzing time of flight, as I'm doing here, is very difficult with digital signals due to the high refresh rates required, this circuit focuses on using analog signals and takes the two analog signals from the receiver and the emitter, and it converts them to a much slower analog signal, which is then analyzed by the processor.
The last section of our project is the object detection portion. For the object detection side of the project, we created a custom dataset from the objects we are using in our course. This way we could train our model to detect our custom-made objects. The model we utilized was the YOLO V8 detection model under the PyTorch implementation. This was deployed using the computer vision tool RoboFlow. This is just a quick demo of the machine learning model working in sync with the PyCamera module.
So in conclusion, this project allowed us to intertwine our skills that we gained while at UCF, and we are really proud of the work that has been put into this project, even with some setbacks and challenges. But we were able to find some creative solutions in order to solve all the problems that appeared. And finally, we would like to acknowledge the UCF ECE department for sponsoring us, as well as Dr. Lewe, Dr. Samuel Ritchie, and Dr. Carr, as well as the review committee.